let's take a look again at the path that the SGD took. It seemed to do pretty well, kind of bouncing along here, but then when it got to where the optimum is, it kept bouncing around. If it had gone toward the true optimum there and gotten kind of smaller and smaller, we would have seen that in the black dots for each epoch. So what can we do about that? It's just kind of getting near the bottom of the bowl, but then just kind of jittering around. Not literally around like spiraling necessarily, but just kind of jumping back and forth. So maybe we could tell it to take smaller steps later on in the process. So if it is jittering around, maybe it'll just jitter less and less and less. You might ask, why is the non-stochastic gradient not doing that? Well, the gradient length is getting smaller and smaller as you get toward that optimum point, so that's why it's not having that trouble. But we could go and say, instead of a learning rate power of 0, which we were using before, no decay of learning rates, let's use a learning rate power of 0.5, and let's run all that. The same thing we were using before. Before we had a learning rate decay, so we could use large learning rates initially and make good progress, and also avoid the danger of just having the optimization diverge. But now we're saying, hey, maybe the learning rate decay can help us near the end, help us kind of settle down to a point. So we'll see what the graphs look like here. So now that we have learning rate decay, let's look at the plane steepest descent. It's doing the same basic thing, but we're still we're graphing a red plus every 100,000 epochs. Now it's taking a lot more epochs to get there, so that was the downside of the learning rate decay. When we didn't have learning rate decay, it zigzagged more, but it made it all the way here in like just 1,000 epochs. So let's see what the SGD is doing now. Okay, so now they look pretty similar, and the red pluses pretty much align with each epoch. Here we're doing 1 red plus per 1,000 epochs of non-stochastic gradient. Sorry, not 1,000. However many mini batches. So I think 50. So they look a lot more similar now, and if we look at how's the actual coefficients that we're using tracking each one, that's looking reasonable. Learning rate decay in the non-stochastic case helps us avoid diverging, and in the stochastic case helps us focus in on the actual optimum even better. There are other ways to help us focus in on the actual optimum without the jittering that we'll talk about later. One thing we need to talk about here, though, is how am I doing the learning rate decay? Am I doing it per epoch or per iteration, like per mini batch? Here it's programmed to be per mini batch because we're just taking steps here. This is indexing the number of steps. But other places say we should do it per epoch. So let's try that, and we'll re-execute that code. Actually, let's just run it all. And then let's see how that turns out. So remember, this is with learning rate decay and decaying per epoch rather than per mini batch. So it seems like we're still doing a good job converging to actual value here. And let's take a look at this history of objective function values. Again, this is a semi-log y plot, so if we see linear behavior here, that's exponential decay. It looks like it's doing a good job. The black dots, remember, are every epoch. The blue is what we're getting in between epochs from each mini batch. And here, it's kind of surprising. The SGD is actually getting toward that final value sooner than the non-stochastic gradient. And we'll see that in the next plot. Here's the zoom in. You can see that jittering is much lower. Here again, the SGD is getting toward that asymptotic value of 0.77-ish, much sooner than the non-stochastic is. That seems strange. Like, how is it that stochastic, which is in some sense worse than non-stochastic, how is it that that's converging faster? Well, we're doing we're decaying the learning rate per epoch here, and we're making steps in between each epoch. So it's like we're using a higher learning rate because all the way through here, the learning rate hasn't decayed from here to there. So it's letting us use higher learning rates, but still with some learning rate decay. A way to think about the trade-off is um, if I trust each stochastic gradient step as much as I trust each non-stochastic one, then I should let them decay at the same rate. If I have less confidence in each stochastic one, maybe because I'm taking super small mini batches, then I should decay per mini batch rather than per epoch. So there's all these trade-offs about how much do you trust each not so good step.